Hi, and welcome to D6 Complex Accelerated Systems. This will be our last lesson in dynamics, and then we're going to move on. There is no new content. We're just looking at subtly more and more complex systems as we go through. So there's nothing really to write down in terms of notes. We're just going to do, I think, 3 examples. Example 1 is about an Atwood machine. So if you take a quick look at this diagram where you have two masses that are suspended over this guy, and this circle here is just a quick representation of a pulley. It's a massless, frictionless pulley, so you can imagine it doesn't have any mass, doesn't have any friction, it spins freely. Is what we do. So if you see one of those circles, independent of size, we're just going to assume that it's a massless, frictionless pulley. And an Atwood machine is two masses suspended off this pulley so that when it's released, the masses can go up or down. So in this case, we have a 6 kilogram mass and an unknown mass are being held in place as shown. And then if the 6 kilogram mass accelerates down at 7 meters per second squared, when it's released, what is the unknown mass? So this little 6 kilogram mass here is going to be going down at 7 meters per second squared, or will be accelerating downward at 7 meters per second squared. So the first thing, of course, we're going to have to do, consistent with the rest, is we're going to have to draw a free body diagram. I'm going to call this mass 1, since this guy over here is obviously mass 2. And on mass 1, what we have is a force due to gravity going down, and there's a string tied to the top which will slow it down, so there is a force due to tension going up there as well. And we're going to end up with 2 forces due to gravity, so I'm going to call that 1. On our second mass, and maybe I'll put a little 1 there just to remind us that that's 1. It's going to look almost exactly the same. This is FG2, and then we're also going to have an FT. Notice how it's the same string that goes up and over and around. And I'm going to maybe not draw that in red because red means forces. Let me try and erase that again. I'm going to do it blue, up and around and down. And since it's the same string, both of my forces of tension will again be equal. They're an action-reaction pair. Every action has an equal and opposite reaction. If I look at my diagram, though, it looks like they're both going in the same direction. They're both going up. And this should give us a little bit of a hint as to how we're going to take a look at our sign convention for this problem. So if I look at the pulley, it's sort of like the last examples we did where we took our head and we tilted them and our X and Y axis were on a tilt. What we're going to do is we're going to use the string as our axis this time. So notice how the string goes around a corner. So on this side, up will be positive, but as we come around the corner on this side, down is positive. And we're allowed to do that because it's moving along the plane. This is called the plane of motion. So our plane of motion we're going to call positive. It's accelerating in that direction. Which means, and if I want to, I can take these forces and I can add them here, just because it might be a bit better. It might be cluttered, but I'm going to take that chance right now, just because I think it's a little bit better to show it with the string and everything on it. And I'm going to get rid of then this green bit. And this is FG1, which means if I take a look at the sum of my forces on my entire system, and that's going to be equal to my mass on my system times its acceleration. It means that I will have a positive FG1. It's going down on this side, so that's a positive. FT is negative on that side, and these are both of my forces on block 1. And then on block 2, I've got a positive FT and a negative FG2. And so these are both of my forces on block 2. And that's going to be equal to M1 plus M2 times my acceleration. I'm going to get rid of those 1s and 2s now that we've used them. mg1 is or fg1 is an m1g minus f2t. Oh, sorry, there's no point in writing that down because we've got a positive and a negative, which means they cancel. So I've got a minus m2g is equal to m1 plus m2 times our acceleration. Now, to me, all of the hard physics is already done. I have chosen quickly to look at my whole system because I didn't know what my force of tensions were, and they didn't ask about them, and I know by now, if I've done enough of my practice problems, that if I look at the whole system, our force of tension is an internal force and it should cancel out. So I looked at my whole system, and then I've got all my forces down, and I've substituted all of my formulas in, and now I notice, though, that if I'm looking for M2, it's in 2 places, so I can't just solve for M2. I'm going to have to now do a little bit of some more complicated math. I'm going to multiply A into my brackets, so I end up with an M1G minus M2G is equal to M1A plus M2A. I'm going to get both of my terms with M2. Sorry, I drew a dot at the wrong one. Both of my terms with M2 on the same side. So I'm going to add M2G to both sides and subtract M1A from both sides. And I think I get an M1G minus M1A is equal to an M2A plus M2G. So now I have both of my M2s on the same side of the equation, and I can factor it out. It is a common it's a common factor in both of those on my right-hand side. I end up with an M1G minus M1A is equal to M2 factored out. I'm left with A plus G. A little bit of rearranging, and I get my M1G minus M1A divided by A plus G is equal to M2, our unknown mass. M2 then is equal to, and I can factor my M1 out if I want. It just saves some trouble plugging stuff into the calculator. M2 is then going to be equal to my 6 times 9.8 minus 7 divided by 9.8 plus 7, and I get the M2 is equal to 1 kilogram. It's kind of fun. I don't know how I ended up with a whole number there, but it turns out I did. Let's look at example number 2. A 3 kilogram mass is tied to a 4 kilogram mass as shown below. If the acceleration of the system once released is 2 meters per second squared, what is the coefficient of friction between the 3 kilogram mass and the table? So I'm going to add that in here. What is mu here? Notice how my 4 kilogram mass isn't rubbing on something, so there will be no force of friction there, but I have a force of friction between my 3 kilogram mass and my table. I'm going to go ahead and not draw a separate free body diagram this time. I'm just going to put my forces onto this diagram. So what I've got for my 3 kilogram one is I should have a force of friction pulling it backwards because I have a coefficient of friction there. It's asking me what it is. And I'm going to have this force of tension pulling it forwards. That same force of tension as it travels over the pulley is going to be slowing down my 4 kilogram mass that's suspended over the corner, and of course there will be a force due to gravity pulling down on that. Of course I have forgotten to add my force due to gravity on my 3 kilogram and my normal force there. And that would be a fairly complete free body diagram. We're going to do the same trick as last time, and we are going to call our plane of motion our positive direction, which means that this is going to be our positive direction. That's our plane of motion. Notice how FF, FT, this FT, and this FG, all 4 of those are in the plane of motion. FN and FG are perpendicular to the plane of motion. So when I look at the sum of my forces on my system, the sum of my forces on my system is going to be equal to my mass of my system times its acceleration. When I look at the forces that are in my plane of motion, I'm going to start at the left-hand side and work my way right, just to make sure I've got all of them. I've got a negative force of friction. I've got a positive force of tension. I've got a negative force of tension. I've got a positive force due to gravity on, which block is that? Let's call this block 1 and this block 2. So I've got force of gravity on 2, and that's equal to m1 plus m2 times the acceleration, m1 plus m2 being the mass of my system. Force of friction, straight off of our formula sheet, is a mu Fn. Positive Ft and a negative Ft cancel. I'm just left with plus Fg2 is equal to m1 plus m2 times my acceleration. It is not, that 3 kilogram mass is not moving up, it's not moving down. So those two forces, there are only two forces there, they must be balanced. So Fn must be equal to Fg in this case. So I get a negative mu Fg1 plus Fg2 is equal to m1 plus m2a. And I'm feeling a little bit crowded here, so I'm actually going to take this line of algebra and I'm just going to move it down out of the way so I get a bit more space. Yeah, I feel better about that already. Negative mu m1g plus m2g is equal to m1 plus m2. Those are in brackets times a, and somewhere along the line I dropped those brackets, so we'll put them back in. I am solving for mu. So what I'm going to do is I'm going to subtract m2g from both sides. Negative. Oh, my pen stopped working for a minute. Let's hope that it comes back to life. Oh, no. There we go. I think it's back. I'm going to subtract m2g from both sides and divide by m1g. And I think I end up with mu is equal to m2g minus m1 plus m2a divided by m1g. Go ahead and practice that algebra on your own. Double check that I am right. And then I think I end up with a 4 times 9.8 minus 4 plus 3. My acceleration being 2 divided by 3 times 9.8. And I should end up with mu is equal to 0.857. Just like that. Coefficient of friction between the 3 kilogram mass and the table, 0.857. Let's look at our final example for this unit. Two masses are arranged as shown on frictionless surfaces. What is the tension in the string that ties them together? So this is kind of like the hardest one we're going to do. I'm going to add this in now because I forgot to, but we need to know that this is a 43-degree angle, and we need to know that this angle over here is a 22-degree angle to complete the question. I'm going to go ahead again, and I'm going to draw my forces over top of this diagram. I've got my force of gravity going down. I've got no force going that way. I've got my normal force perpendicular to the surface, and I've got my force of tension traveling up towards that pulley. I'm going to have the same force of tension pulling this way because they are an action-reaction pair. I'm going to call this guy a 1. So this is box 1. I'm going to call this box 2. I've got my force due to gravity going down on box 2, and then I've got my normal force perpendicular. Again, I am going to call the direction of motion my plane of motion. Plane of motion, and I actually don't know which direction this is going to move at all. I have this 7 kilogram mass, which is lighter, but is on a much steeper incline than this 10 kilogram mass, which is heavier, but on a flatter incline. So I have no idea. I'm just going to arbitrarily decide a direction of motion to be positive, and I'm going to call this direction positive. We are not on a flat ground, which means any forces that are not in what we've decided as our positive plane, if you're not parallel or perpendicular to that plane of motion, we are going to have to split it up into components. So I'm going to, maybe I'll draw this just a little bit bigger so that we can see it a bit better. This is my FG1. We're going to have to split it up into components that are parallel to the surface and perpendicular, and we know that this is going to be theta. That'll be our angle right in there. I'll just leave it out. Well, now let's leave it in there. That's our theta, and since this is FG1, I'm going to call it theta 1. We're also going to have to split the right-hand one up into parallel and perpendicular. This will be our theta 2. Which means that this will be FGY, this will be FGX, this will be FGY, this will be FGX, and this should be a 1, that should be a 1, this should be a 2, that should be a 2. And that is all of the forces and components that we are going to need. So, we are asked about the force of tension, but I know from now, because I've done enough of these for practice, that if I just look at one of them, I'm not going to know the force of tension and I'm not going to know the acceleration. This system will accelerate when it's released. So what I'm going to have to do first is I'm going to have to look at the sum of my forces on my system. And that's going to be equal to my mass of my system times its acceleration. I'm going to look at the forces that pull it left and right, and I'm going to start at the left-hand side on box 1. On box 1 to the left, I have a force due to gravity, just the x component pulling it down the ramp, and I have Ft that's going to be slowing it down. So I've got a positive Fgx1 minus Ft, and those are the only two forces in the plane of motion on box 1. On box 2, I've got a positive Ft, and I have a negative Fgx2, and that's going to be equal to the sum of my masses times its acceleration. Again, my forces of tension cancel, which is perfect, and my Fg1x is an opposite component. You can prove this to yourself if you want, but it's going to be an Fg1 sine theta 1 minus Fg2 sine theta 2 is equal to m1 plus m2 times a. If I solve for my acceleration, I get an m1g sine theta 1 minus m2g sine theta 2, all divided by my sum of my masses. I think if we substitute some values in, I get a 7 times 9.8 times the sine of 43 minus 10 times 9.8 times the sine of 22, all divided by 7 plus 10. And I get that my acceleration is 0.5925 and a bunch of other decimal points, which I'm going to keep in my calculator, but not write all the way out because it'd be a pain in the butt. So I was going to leave it like that because it's not a final answer. So then to find the tension, I could either look at box 1 or box 2. I've arbitrarily decided to look at box 1 so that I've got an Fgx1 and an Ft. So if I look at the sum of my forces on box 1, I'm running out of space, so I got to be careful, is equal to m1a. I've got some of my forces, which I just talked about, are going to be an Fgx minus Ft is equal to m1a. My Fgx from up above is my m1g sine theta minus Ft is equal to m1a. If I move some stuff around a little bit, I get that Ft is equal to m1 times g sine theta minus a. I did 2 steps in one there, but I'm pretty sure if I algebraically rearrange that properly, that's what we turn out with, which is a 7 times 9.8 sine 43 minus what we found above for my acceleration, 0.5925, and I'm going to put those ellipses in to indicate that I'm going to use that whole number that I have stored in my calculator there, and I get that my force of tension comes out to be about 42 newtons.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.